I want to freshen up on my chemical engineering principles.
Sure. Where would you like to start? We could cover topics like mass and energy balances, thermodynamics, fluid mechanics, or something else.
Yes, we want to see the comparison between fluid mechanics, Reynolds number mechanics, Reynolds fluid mechanics, dimensionless numbers, and heat transfer dimensionless numbers, and the mass transfer heat transfer dimensionless numbers, and the comparison between these different dimensionless numbers.
That sounds like a great plan. We can compare Reynolds number in fluid mechanics with Prandtl number in heat transfer and Schmidt number in mass transfer. They all have similar roles in characterizing transport phenomena. Would you like me to elaborate on any of those?
Yes, some comparison, please.
We can definitely compare those. Are you interested in the specific formulas, their physical interpretations, or how they relate to each other in different contexts?
Yes, I mean how they exactly relate to each other.
Many of these dimensionless numbers are related by analogy, representing the ratio of different forces or transport mechanisms. For instance, the Reynolds number compares inertial forces to viscous forces in fluid flow, while the Nusselt number relates convective to conductive heat transfer, showing analogous behavior in transport phenomena. Does that make sense? Or would you like more examples?
Yeah, for mass transfer, what is that exactly?
For mass transfer, a key dimensionless number is the Sherwood number, SH. It's similar to the Nusselt number, but for mass transfer, representing the ratio of convective mass transfer to diffusive mass transfer. Another important one is the Schmidt number, SC, which compares the momentum diffusivity to the mass diffusivity, relating fluid properties directly.
Yes, now tell me what is the equivalent of like a number in the heat transfer, dimensionless numbers in the heat transfer. Equivalent of that Schmidt number.
The equivalent of the Schmidt number in heat transfer is the Prandtl number, PR. The Prandtl number compares the momentum diffusivity to the thermal diffusivity, much like the Schmidt number compares it to the mass diffusivity, showing the analogous relationship between momentum and heat transport.
Now, is there any similar number in the fluid mechanics also, like Schmidt number?
In fluid mechanics, the Mach number is quite significant, though not directly analogous to Schmidt or Prandtl numbers. The Mach number compares the speed of an object or fluid to the speed of sound in the medium, which is vital for understanding compressible flow.
Okay, now you are talking about the convective. We are talking about now the convective heat transfer. I'm talking about there's something called forced convection and free convection.
That's right. Forced convection occurs when an external force, like a fan or pump, induces fluid motion, while free or natural convection happens due to density differences caused by temperature gradients. Are you interested in the dimensionless numbers that govern these?
Yes, what are those comparative numbers? Yes.
Forced convection is when fluid movement is driven by an external factor, like a pump or fan. The relevant dimensionless numbers typically include the Reynolds number to characterize the flow. Free convection, or natural convection, happens due to density differences caused by temperature gradients, and the Grashof number is crucial for that, comparing buoyancy forces to viscous forces. Does that clarify things?
What is the Hatta number in the mass transfer?
The Hutton number, Ha, is a dimensionless number used in mass transfer to relate the rate of chemical reaction to the rate of diffusion. Essentially, it helps you determine whether the overall process is limited by the speed of the reaction or the speed of the diffusion.
Yes, I think. Can you tell me about the osmosis and reverse osmosis also? Okay, let it go. Process dynamics and control, please.
In process process dynamics and control, key equations often involve transfer functions, which describe the relationship between input and output signals in a system, often expressed in the Laplace domain. The basic equations are derived from fundamental principles like mass and energy balances, incorporating terms for deviations from steady state. Are you interested in specific types of control systems?
Provide some equations of relevant dimensionless numbers.
It is great to see you diving back into the core of chemical engineering. The beauty of transport phenomena lies in the triple analogy. The fact that momentum, heat, and mass transfer often follow the same mathematical patterns. Here is a breakdown of the essential dimensionless numbers and the equations you need to freshen up. 1. The big three comparison. Convective transport. These numbers compare the total transport, convection plus diffusion, to just the molecular diffusion. Transport type, dimensionless number. Equation, physical significance. Momentum, Reynolds, RE, closing parenthesis. Inertial forces versus viscous forces. Heat, Nusselt, NU, closing parenthesis. Convective heat transfer versus conductive heat transfer. Mass, Sherwood, SH, closing parenthesis. Convective mass transfer versus diffusive mass transfer. 2. Fluid property ratios. These numbers tell you how thick the respective boundary layers are relative to each other. Prandtl number, PR, relates momentum and heat. Schmidt number, SC, relates momentum and mass. Lewis number, LE, relates heat and mass. 3. Natural versus forced convection. You asked about free natural convection. In these cases, we replace RE with the Grashof number. Grashof number, GR, the Reynolds of natural convection. Rayleigh number, RA, often used to determine if the natural convection flow is laminar or turbulent. 4. The Hatter number, HA, closing parenthesis. The Hatter number is specific to mass transfer with a chemical reaction. It tells you if the reaction happens in the film or in the bulk liquid. If H are greater than 3, the reaction is very fast and occurs entirely in the liquid film. If H are less than 0.3, the reaction is slow and occurs in the bulk liquid. 5. Process dynamics and control, PDC. For PDC, we move from fluid properties to time domain and Laplace domain equations. First order transfer function, where K underscore P is gain and tau is the time constant. PID controller, time domain. Dead time, transport delay. A quick note on your Mach number question. In fluid mechanics, the Mach number, MA equals version/A, relates flow speed to the speed of sound, compressibility. In heat transfer, the closest relative is often the Peclet number, PE equals RE times PR. While Mach relates to wave propagation speed, Peclet relates the rate of advection to the rate of diffusion. If PE is very high, heat is carried by the fluid much faster than it can diffuse, similar to how a high MA means the object moves faster than the pressure waves can warn the fluid ahead. Would you like me to dive deeper into the Chilton-Colburn analogy which mathematically links J underscore H and J underscore D factors?
No, not now exactly. Let me see. There is something called Modi chart, I think. Modi chart for friction factor and Reynolds number. Or something Cox chart or something. Please elaborate.
Actually, there might be a slight mix-up in the names, which happens to the best of us. A Cox chart is typically used to plot vapor pressure versus temperature. When we talk about the relationship between the friction factor, F, and the Reynolds number, RE, we are looking for the legendary Moody chart, or Moody diagram. This is the bread and butter of fluid mechanics for calculating pressure drop in pipes. The Moody chart, friction factor versus Reynolds number. The chart plots the Darcy-Weisbach friction factor, F, against the Reynolds number, RE, for various levels of relative roughness, epsilon D.
Yes.
Key equations for the chart. Depending on where you are on the x-axis, the Reynolds number, the physics, and the equations change. 1. Laminar flow, RE less than 2100, closing parenthesis. In this zone, the roughness of the pipe doesn't matter. The friction factor is purely a function of the fluid's momentum and viscosity. Note, if you are using the Fanning friction factor, it is F equals frac 16 RE. 2. Transition region, 2100 less than RE less than 4000. Closing parenthesis. This is the no man's land. The flow is unstable, switching between laminar and turbulent. It's hard to predict F accurately here, so engineers usually design to avoid this range.
Yes.
3. Turbulent flow, RE greater than 4000, closing parentheses. Here, the friction factor depends on both RE and the pipe's internal roughness. To find def mathematically, since the chart can be hard to read, we use the Colebrook-White equation. At very high RE, the flow becomes fully rough, and the friction factor becomes independent of RE. The lines on the chart go flat. For smooth pipes, we often use the Blasius equation, valid for 4000 less than RE, less than 10 to the power of 5,
Yes.
closing parenthesis colon. Why this matters? Once you find F from the chart or equations, you plug it into the Darcy-Weisbach equation to find your head loss. H_L, closing parenthesis colon. Since you mentioned process control earlier, would you like to see how we use these friction calculations to size a control valve or determine pump head requirements?
Okay, maybe pump head requirements, but now for now, Nusselt number is what exactly for free convection in terms of Prandtl number and Grashof number.
In free natural convection, the Nusselt number, Nu, is primarily a function of the Grashof number, Gr, and the Prandtl number, Pr. The most common way to express this relationship is through the Rayleigh number, Ra, which is defined as the product of the two. The general correlation, for most geometries, the empirical correlation takes the following power law form. The constants C and N depend on the geometry of the surface, vertical plate, horizontal cylinder, etc., and the flow regime, laminar or turbulent. 1. Vertical plates and cylinders. For a vertical surface of height L, the correlations are typically divided by the Rayleigh number. Laminar flow, 10 to the power of 4 less than Ra less than 10 to the power of 9. In this regime, the boundary layer is stable and thickening. Turbulent flow,
Yes,
10 to the power of 9 less than Ra less than 10 to the power of 13. In the turbulent regime, the heat transfer coefficient, H, becomes independent of the characteristic length,
Yes,
L.
correct.
2. The Churchill and Chu correlation. If you need a single equation that covers the entire range of Rayleigh numbers, from laminar to turbulent, for a vertical plate, this is the gold standard. Physical interpretation, GR, Grashof, represents the ratio of buoyancy forces to viscous forces. It plays the role that the Reynolds number plays in forced convection. PR, Prandtl, represents the ratio of momentum diffusivity to thermal diffusivity. Nu, Nusselt, tells you how much the heat transfer is enhanced by the fluid motion compared to pure conduction. Summary table for quick reference.
Physical interpretation is very
Flow
important.
regime, Rayleigh range, Ra, constant, C, exponent, closing parenthesis, laminar 10 to the power of 4 minus 10 to the power of 9, 0.59, 1 quarter. Turbulent 10 to the power of 9 minus 10 to the power of 13, 0.10, 1 third. Since we are talking about buoyancy, would you like to look at the equations for the terminal velocity of a particle falling in a fluid, Stokes' law, or perhaps move into the mass transfer equivalent, Grashof for mass transfer?
Okay, no, right now I want Nusselt number for forced convection in terms of Reynolds number or Prandtl number again. Forced convection.
In forced convection, the Nusselt number, Nu, is a function of the Reynolds number, Re, and the Prandtl number, Pr, because the fluid motion is driven by an external force, like a pump or fan, rather than just buoyancy. The general empirical form is 1. Flow over a flat plate, external flow. The correlation depends on whether the boundary layer is laminar or turbulent. Laminar flow, Re_x less than 5 times 10 to the power of 5, valid for PRGEQ 0.6. Turbulent flow, Re_x greater than 5 times 10 to the power of 5,
Yes,
valid
correct.
for 0.6,
Correct.
less than PR less than 60. 2. Flow inside a pipe, internal flow. For fully developed turbulent flow, Re greater than 10,000. The most famous equation is the Dittus-Bolter equation.
Bolter equation.
N equals 0.4 for heating of the fluid. T_wall greater than T_bulk. N equals 0.3 for cooling of the fluid. T_wall less than T_bulk. 3. The Cedar-Tate correlation. If there is a large temperature difference between the wall and the fluid, the viscosity changes significantly. In such cases, we use this version, which includes a correction factor. where mu is the bulk viscosity and mu_w is the viscosity at the wall temperature. 4. Comparison to the mass transfer equivalent. To see the triple analogy in action, look at how the Sherwood number, SH, mirrors these equations by replacing PR with the Schmidt number, SC. Heat transfer, forced. Mass transfer, forced. Nu equals FRE_PR. SH equals FRE_SC. Nu equals 0.023 times RE_, the power of 0.8, times P, RTO, the power of 0.33. SH equals 0.023 times RE_, the power of 0.8, times S, CTO, the power of 0.33. Physical meaning. Reynolds, RE, measures the strength of the forced flow. ASRE increases, the boundary layer gets thinner, and NU, heat transfer increases. Cranvley, PR, measures the fluid's inherent ability to spread momentum versus spreading heat. Would you like to see how the Colburn J factor ties these together into a single universal analogy for engineers?
Okay, thank you very much right now.